Good morning, everyone. Thanks for coming for this session. My name is Aalvaro. I'm from Brazil. Came all the way down here, so it's nice to be here. I'm a Google developer expert for IoT. I'm also a GDG organizer, so it's awesome to see those events organized by GDG. I'm a product engineer at Leverage. Actually, I work for a company here in the US. I work remotely. Leverage have offices in Rockville and Baltimore. So we have open positions. So there we work with just IoT projects. So if anyone likes IoT, it's a good opportunity to work with us. And all my slides and content are on my website. So it's this one. I will put the link in the end. Those slides are not there yet, but I'll upload later. Today I'm going to talk about edge computing with a bit of IoT, machine learning, and cloud computing. How many of you heard about edge computing? Can you raise your hand? No one? Well, one. Well, here's the breakdown of what we are going to cover. First, I'll give some concepts about edge computing. Then I'm going to show a practical scenario applying all those concepts. And also, I'll show how to build this scenario. So first, in the beginning, we started using like local and centralized data centers for like processing things and doing our apps. And then we moved to use remote servers, and that's what we call cloud computing. So we made that shift due to better availability, reliability, and also ease of maintenance, and also to save costs because having like a local data center, you have to invest a lot of to buy hardware, and you have to spend a lot of money managing this infrastructure. With the cloud, we can start small, and our business can grow, and our infrastructure can grow with our own business. So as we get more clients and close more deals. So that's a nice thing about cloud computing. But when we talk about edge computing, we are bringing back the idea of having, again, local servers, or also use edge device like smartphones nowadays have a lot of processing power. So we are trying to process things close to where they are being generated, close to where the data is coming. So that's the idea of edge computing. So let me show some examples of when to apply edge computing. So when does it make sense? So first thing, privacy. Let's say that we want to keep track of how many people are inside of a building. So we can spread a lot of cameras and send the videos and images to the cloud because we have a lot of processing power there. But we are going to have like huge problems because we are saving user data. And in the end, it's not what we want. We just want to know how many people are inside of a building. We want to keep track of those persons there. We can harness the power of local processing to just get the head count, the persons that are inside of a building, and send that processed data to the cloud. So in that way, we are not saving users' data, and we are good with privacy. So that's one example of using edge computing to improve privacy of our projects. And in that same example, we are saving a lot of bandwidth because if we are going to send like, again, video streams and images to the cloud, that is going to take like huge cost to save all of that data. So another example of using edge computing to save bandwidth, it's voice assistants. Usually for the activation word, all of that is processed locally. So when you say like, hey Google or Alexa, this is processed on the device, and later the other part of the conversation is going to be processed in the cloud. So in that way, the device does not need to be all the time connected to the internet. And Google also announced this year that the next generation Google Assistant is going to have a feature to work entirely offline. So it's all the processing of the natural language processing is going to run offline on the device. So with that, we are going to save even more bandwidth and also have better latency and reliability of the voice processing. So that's another thing, like having lower latency. So let's take an autonomous car, for example. Autonomous cars have to use a lot of sensors to detect like distance and track people that are around cars and to know where if it needs to like turn to the left or go straight and those kind of things. And cars need low latency to react fast to things that are happening. So to avoid, for example, an accident and those kind of things, it cannot rely on cloud computing. It needs to process things locally. So usually those cars have like built-in GPUs to run machine learning inferences. So that's an example of edge computing. And of course, those cars still rely on some things to the cloud, like they can send telemetry to the cloud, so you can like monitor your car from remotely. And also those cars receive like OTA updates to be improved and those kind of things. So yeah, we're still using like edge computing and cloud computing to make better products. And also reliability. So let's say that we want to like control a house, or for industrial control, we want our house to also work just locally. I don't want to like, I want to turn on and off my lights, and if I don't have internet, I cannot do that. Like, what kind of product is that? So it'd be awesome if like automation rules can run all locally. So we can apply edge computing to do that. But of course, we still want to control remotely. We still want to have like real-time data to be accessed remotely, and this is going to be saved on the cloud, and we can do other kinds of stuff sending that data to the cloud. And in the end, we're going to save a lot of money because, for example, if we're running machine learning inferences in the cloud, we usually need to rely on GPUs, and those are really expensive to use in cloud. So we can harness the power of the smartphones or other types of edge device to do that. So talk is cheap. Let's show this in practice. The idea here is to show how to use cameras as general purpose sensors, not just for images, but also get data from that image and be able to identify things with that. So my example here, I spread a lot of cameras through a house. So I can detect, for example, when someone arrives at home. So if I detect a car, I can trigger something. Or also I can trigger scenes if someone's inside the bedroom, so I can detect occupancy. Or also, for example, if there's a cat at the kitchen, be sure to check if a person is there, so the cat's not going to steal something from the fridge. So it's good to know that. So on the example that we are going to build here, we are going to be able to do that. So the idea is to use cheap Wi-Fi cameras because we are going to spread like a lot of cameras through a house. We are going to have a local server to process the images and run machine learning inferences to detect objects. And then we are going to send just the processed data to the cloud. We are not going to send images. And we are going to have like a local interface where we can see the images just locally and also the inferences that the local server is running. But also have a remote interface that sends that data to the cloud, and we can see just the processed data. So here's the breakdown of the architecture they are going to see. I'll not enter in much details right now because we are going step by step on this project. So for the hardware part, we are going to use some ESP32 cameras. ESP32 is one of those king of IoTs because a lot of projects have been using them because they are cheap. And now they have this module that comes with the camera that can be found around $9 and $10. So it's really cheap for a device with Wi-Fi, Bluetooth, and it's even dual core, this microcontroller. So it's really nice and have the built-in camera. So that's the device that we are going to use to get the images. And we are going to use a Raspberry Pi 3 to process those images and run machine learning inferences to process that data. So the objective of the cameras are just to provide the images on the local network. So it's really simple. So those cameras are going to connect to Wi-Fi, provide a HTTP interface to provide the image, and also read the image from the camera sensor. But I add a nice feature. So the cameras can be found on the network automatically, instead of knowing the IP address of the camera and have to register that IP to the server. So I used a protocol called MDNS. So basically with MDNS, you inform a service name, in which case I provide the name camera. And also you choose the protocol that you are using. That can be UDP or TCP. In that case, I use TCP. So in that way, I can use like the device ID .local/JPG. Instead of like using the IP address of the device to access the image. So here's, you can also debug locally. There's a CLI called DNSSD that you can search for MDNS services. So here I'm searching for a camera. services. And as you can see, I'm finding 4 cameras in my local network, so which is nice. And the server is going to use that to find the cameras automatically. And also, I'm accessing the URL here and getting the images from the camera. So I don't need to type the IP address, like I said, just the device ID.local/JPG. So that's it for the cameras. Now I'm going to go to the local gateway that's running on the Raspberry Pi. Well, the objective of the local gateway is to fetch those images from all the cameras that are on the local network, classify them, and send the processed data to the cloud. So in this case, I use a Raspberry Pi, which is a single board computing. So we can run, it usually runs on a Linux OS. So we can use any language as you want. You can use Java, Python. In this case, I use Node because I like Node and like to code in JavaScript. So, and also I'm using the TensorFlow library. The JavaScript version is TensorFlow.js. In my opinion, is one of the easiest way to start with machine learning in general. And I will show why is that. But first, I want to make a disclaimer. I'm not a machine learning expert at all. So if I say something wrong, please tell me after this talk. Or also, sorry if I say something wrong, but I'm not an expert. But maybe that's the best part of this talk, because it's so amazing how many things we can do with machine learning nowadays without having a deeper knowledge of machine learning. And one of the reasons, for example, for TensorFlow.js, we have a lot of pre-trained models available to be used for text classification, for image, to work with image, for text to speech, speech to text. So we can use those pre-trained models to build our own projects without having to have a deeper machine learning knowledge. As we are working with image, there are 2 types of machine learning models to work with that. There are classification models and object detection models. For classification, TensorFlow.js provides the MobileNet model that basically gets an image and classify the whole image as one label. So for example, on the left image, the model have a higher confidence that it's a cat and a lower confidence that it's a dog, for example. So it's just one label that's going to be classified as the highest one. But for object detection models, they use a classification model under the hood, but they use a sliding technique to detect objects and classify them. And another difference that usually classification models can classify more labels, like MobileNet classify 1,000 different labels, and Coco's SSD, which is an object detection model, classify just around 100 different labels. But as you can see, the output of the object detection model on the right image, it can detect like 2 cats, a dog, and a duck, for example. So it's much more powerful. And it's the one that we are going to use for that project. So here's the code to classify an image using Coco's SSD. There's an NPM model to just import and use some of the pre-trained models that are available for TensorFlow.js. So I removed some of the boilerplate, but it's not much bigger than that. So it's so awesome that we can like classify images with just a bit of code. And let's see again the architecture of the local gateway. So the Raspberry Pi is going to search the image using MDNS. So it's going to find all the cameras that are available on the network, and then are going to process those images using TensorFlow. And it's going to provide also a local interface so we can see the images that are being classified. And after that, we are going to send the data to the cloud using the MQTT protocol that we are going to see later, the cloud architecture. So here's the breakdown of the classes that the gateway uses. I will not go in much details here because you can see later the source code. All this project here is open source, so you can take a look later at the code. So it's all available on my GitHub account. So let me show you how the local gateway is working with the cameras and the Raspberry Pi. So here's the server when it cannot find any cameras. So it's showing like doesn't find any cameras providing the MDNS services. But here's when it's working. So as you can see on the left image, I just entered on my office. and it detects a person and a laptop. As you can see, it's pretty fast. So it was able to detect some of those objects. On the middle image, it's my cat on my kitchen. So it's really good to detect cats. And the last image is my wife giving some food to my cats. And as you can see, it detects a person and a cat. But also there is a misclassification, like it detected a dog. So we need to remember that machine learning models are not perfect. So sometimes you are going to see like misclassifications. So basically, that's how the project works locally. So we can see the images, we can see the labels that the Raspberry Pi is classifying. And yeah, that's it. And performance-wise, here's a small tip for you if you're going to start with TensorFlow.js. So TensorFlow.js have like the core library, which is made with JavaScript, but they also have 2 other versions made with Node, and also a version for Node with GPU. So the version with just JavaScript does not have like a good performance. So on my computer, it was taking like 8 seconds per frame to detect the objects using this model. And on the Raspberry Pi, it was even worse, like 45 seconds to classify just a frame. But using the Node.js bindings, it's a bit hard to, on a local computer, it's easy to do, but for like a device like Raspberry Pi that have an ARM processor, I took some time to build the TensorFlow Node version to the Raspberry Pi. But I got some really good results. So running on a Raspberry Pi was taking like 1 second to detect objects on each frame. So for me, it's really good. And on my computer, it was taking like 1 to 200 milliseconds to classify an image. And I didn't try the Node GPU version because I don't have a GPU, but probably have a much better performance, and maybe we can do like 60 frames per second, so it's like real-time object classification. For the cloud setup, I use Google Cloud, and I use a service that it's more towards IoT devices. It's Cloud IoT Core. I will show you why I choose to use it. So after the data arrives on Cloud IoT Core, that goes to a PubSub topic. And then I set up a cloud function to process that PubSub topic, which also stores the data on Firebase. Because Firebase is really easy to use. It's a NoSQL database. We can put whatever data we want to put there. And Firebase is going to be used as the source of the remote web interface. So the user will be able to access that data remotely. So here's Cloud IoT Core. Cloud IoT Core allows devices to send data over MQTT and HTTP, which are protocols that are used a lot for IoT devices, but also it has like a security layer. So all devices that are posting data to Cloud IoT Core need to have credentials and those kind of things. But, and I have the cameras register here, but if you remember, the cameras are not sending data to the cloud directly. So that's why I use a feature from Cloud IoT Core, which is for gateways. So I registered the Raspberry Pi as a gateway here in Cloud IoT Core. So the cameras are sending the data to the gateway, and the gateway is sending the data to the cloud on the behalf of the cameras. So for the backend, it's like the camera send the data directly. It doesn't know that it's a gateway that is sending the data. So that's nice. Maybe for this project, of course, the cameras have Wi-Fi. They could send the data directly, but the cameras cannot process the data. They cannot run machine learning. So in that case, it makes sense to use a gateway. But also in other cases, like for remote sensing, like for, let's think on some end nodes that use RF or LoRa or other types of communication with the gateway, those devices cannot connect to the internet, or a Bluetooth device, for example. So you can use that gateway architecture to also send data using Cloud IoT Core. So to ingest data, like I said, the data is going to arrive on a PubSub topic. So I use Cloud Functions. I'll not go in much details about Cloud Functions because I know that there are some really good talks about serverless computing here at this event. So I hope you guys see one of those. But basically, it's a serverless platform that you just run your code and you don't have to manage servers. So it's really easy to use. It has support nowadays for Node, Python, and Go. So again, I choose Node because I like to code in JavaScript. And here's the code to process the data coming from Cloud IoT Core. So Cloud IoT Core have two types of messages. One is telemetry data, and another one is the state of the device. So for example, I forgot to mention, the gateway also sends some metadata about the cameras. So when the cameras go offline or they come back, the gateway also sends that data to Cloud IoT Core. So I have more information about the cameras that the cameras will not be able to send, because if they're offline, they will not be able to inform that. We have to make like some timers to detect that they are offline or those kind of things. It would be not going to be that easy. So yeah, I made those two cloud functions that react to PubSub messages coming to PubSub. And to store data, again, I use Firebase because of its real-time syncing capabilities, so it's really easy to use. And this is, to be honest, is the complete code of the two cloud functions. I'm not lying here. It's all that you need to save the data that is arriving from Cloud IoT Core to Firebase. So yeah, it's really easy to use. And you just run Firebase deploy, and this is running. It's scaling automatically on the cloud. So it's really easy to use. And also, I made a web interface using Firebase hosting. So I posted on Firebase hosting to show the Firebase data. So here, as you can see, we are just seeing the process data. So the camera found a cat, the other camera found a person. But I also add other features that we can do in the cloud, because maybe we can send like alerts based on rooms. We can like do some better separation between the cameras. So that's what I did. But as you can see, we don't have the image here because we are not sending that. And also we have like the metadata so for example, when a camera goes offline, I can see on the remote interface. And also I have access to the gateway. So if I click on open local monitor, I can open the local web interface that I can see the image and those kind of things. So yeah, so we went through the whole architecture. And if you guys enjoyed this project, I wrote an article about it, so you can just follow the tutorial, and the tutorial have much more details. But for DevFestDC, I made some improvements to that project. So I love cats. I have to be honest with you. My wife is here, will not let me lie. Here are my five cats: Berry, Muffin, Raspberry, Popcorn, and oh my God, I'm forgotten one. And Jan, our first one. So I thought, well, I can use that same architecture to track my cats at my house. So how can we do that? I searched for some tutorials to train a custom object detection model, and I found some really good ones, even using like cloud TPUs to train the model, really easy to follow. And most of those tutorials use a concept called transfer learning. And what is transfer learning? Basically, you're getting a pre-trained model, like for example, for images. The architecture of image classification model after training on the middle layers or the first layer, you probably learn how to detect colors, textures, shapes. So underlying the whole machine learning architecture, you learn a lot of things to work with images. So instead of training the whole model with just like a small data set that I have, I can leverage the knowledge of that other architecture and train just the final layers with my own data. So that's the concept of transfer learning. That's why we can train a good image classification model without having like a huge data set. So I started building my own data set. I used a software called Label Image. So I got like 100, 200 images and started labeling it. So thanks my wife me and her are taking so much pictures of our cats. And I started drawing those rectangles and marking their names. But I have bad news, because my custom object detection model didn't work at all, because unfortunately for an object detection model, I still need to have like at least 1,000 images to have like a good results. So I was like, oh my God, I'll not be able to track my cats. I need to fix this. So I got an idea. So what about training a classification model instead of an object detection model? Because I know that classification models converge easier, and they don't need that much data. So I thought, well, I already built the data set, so I wrote a script that read the same data set and converts to crop the image to have like the cat picture separately instead of having like the whole picture with more than one label. So I convert that, so I got 5 folders with a lot of pictures of my cat, and I used that to train a custom classification model. And I decided to use the best of both worlds. Like the Cocos SD model was really good to detect objects, and inside of those list of objects were cats. So I used the output of the Cocos SSD model to get I filter for the cats and crop the image where the bounding box that it found the cats, and then ran my custom classification model, which I got a really good results in that case. So for example, let me show how it worked. So using my custom cat classification model. So here's an example. I was training using my computer, and I wrote a small script using OpenCV to test with my webcam. So here's Barry going back on my back. So the bigger image is the output of the Cocos SSD model. So it found a person and found a cat. And as you can see, the image was cropped and it found Barry successfully because it ran my custom classification model instead of trying to like do both things at the same time. So yeah, I put 2 models to work together and I got those really good results. So I exported the model that I trained using TensorFlow, the Python version of TensorFlow and Keras, and exported to use with TensorFlow.js and put on my server made with Node. And the same example, on my backyard, it found a cat and also cropped the image and classify as Jen. So it's the right one, so it works. And another case, Barry's at the kitchen, crop the image and classifying it, and it worked. But of course, there are some positions that I don't have on my data set, like my cats, like their back facing me, so I don't have some examples. So now I can build to improve my data set by getting those images of my cats on other positions and retrain the model to get better results. So in this way, I'll have an even better model to classify my cats. But that's basically it. So in this case, as you can see, it found 2 cats, cropped the images, and classify using my other custom model. But I didn't try to use that on a Raspberry Pi yet. I just ran on my computer. I mean, on my computer, it had a good performance. So I hope on the Raspberry Pi also I can also get a good performance. And of course, we can do even more, thinking about edge computing and applying those same concepts that I showed to you here. One example is to use specialized edge computing devices. So Google launched those Coral boards. They have a built-in TPU, which is a tensor processing unit. It's a unit. It's like a GPU, but for tensors, which is the smallest unit of TensorFlow. So they are really specialized on running inference for TensorFlow. So they have like a really good performance. I saw one of those running some examples on Google I/O, so it's mind-blowing. So I can use one of those to get better results on my edge device. There's also other devices that are available on the market, like the SciPid MaxBit. They use like a KPU, which is a neural processing unit that also have support for TensorFlow models. And SparkFun launched the new board this year. It's called SparkFun Edge that have support for TensorFlow Micro, which is a version of TensorFlow for microcontrollers. So it's really nice. They have an example of processing audio in real time using those boards. And of course, we can apply on other contexts, like for example, doing face recognition instead of object detection. So for example, I can generate an alert if someone that is not allowed to enter in a place, or yeah, I don't know, there are some airports that are starting to use those things to allow a person to enter the airplane and those kind of things. So we can do that. There's a really good library made with Python and dlib. It's called face recognition. It's really obvious, the name of the library. I just put a link here so you guys can see later. So yeah, we can change that same architecture to run face recognition instead of object detection. And also another model that TensorFlow.js have as a pre-trained model to be used. It's the PoseNet model that we can like detect the position of the body parts of a person. We can use that to detect, for example, if someone falls in the ground. So if, I don't know, maybe someone had an accident in a workplace, we can use that to generate alerts and those kind of things. So it's a nice thing to do. And wrapping up, like I said, we can harness the edge device processing power, even by deploying a custom server or using like the user smartphone to run some machine learning models. This way we can extract more data where the data is being generated, so we can like get more things and just send the process data to the cloud. But we are still going to continue using the cloud for which is good, like for scalability, for flexibility, and because it's really easy to use and get our business working. So that's basically it. So I hope you enjoyed this session. And if you have questions, I'm here to answer. And here's my website again. So I will post those slides later. Thank you. Questions? Here.
What is the best language for machine learning or image processing? Is that Python or some scripting languages or anything?
The TensorFlow library today they have a pre-built version of TensorFlow for ARM processor, so it's easier to get started. I'm not sure which one have a better performance. That's a really good question because, like I said, I tried both. I didn't notice that much difference because in the end they use like C++ library that have like almost the same performance. So yeah, the important part is to use like the native versions of the bindings for TensorFlow. Because if you use like just the Python version or just the pure JavaScript and pure Python version, they will be really bad with performance. So the downside of using TensorFlow.js on ARM processors that they don't have like a pre-built version of the native dependency. So it took me a while to figure out how to build TensorFlow node for a Raspberry Pi. But it's I have the details on my article, so you can check how to do that.
But we need some library support from Python or scripting languages.
No, you don't need to do anything else to support that.
But transfer this is fully supported.
Transfer learning?
Yeah.
Ah, you want to run transfer learning? I don't recommend to do that because it's a really heavy process. Usually you run like on your computer or you can use even like cloud computing, use a TPU to train like for an hour and have like really good results. But usually to run transfer learning on edge devices is much harder. Usually use the cloud to do that and just deploy the custom model again, like update the model on the edge device. More questions? Oh.
So were you using TensorFlow serving on the edge devices, or were you just using it for image capture?
You can continue. No, I didn't use serving. I'm using raw TensorFlow.js library with my model. I'm not using TensorFlow serving. TensorFlow serving is more like for a backend, more for a backend code to make a model available to be used. So it was not that was not the case. But maybe I could use like for the cameras to use TensorFlow serving to get the results and then send the camera send the process data to the cloud directly. Maybe it can be a architecture that might work. But yeah, I didn't use TensorFlow serving. You mean use other types of device to run?
Does it help speed up like general computation for image processing?
Yeah, they have like much better performance to do that. Like using like TPUs and those kind of things, you have like much better results. Yeah. Like I used to train the object detection model. I use cloud TPUs. Like with 30 minutes, you have like a good custom model trained. Like it's super fast.
I see, but isn't that because you're performing an TensorFlow operation? Like, would it speed up computation? So my question is, would it speed up computation behind TensorFlow computation of TensorFlow operation?
Oh, gotcha. Or not TensorFlow. Well, that's a good question. I don't know how to answer that because I know that those edge devices they have optimizations for tensor tensor operators. Got your questions. Yeah, I don't know how to improve that, but it was the heaviest thing running. The other steps were really light, like just fetch images and send data to cloud was not heavy at all.
So what was your comparing to other development boards like Intel Edison or like Arduino? What landed you at Raspberry Pi, and what possible advantages does Raspberry Pi have over the other development boards? And can I implement this on an Arduino?
Okay, gotcha. Well, I use Raspberry Pi because it's easy to find it and have like the best documentation available. So yeah, there are some alternatives but like the Intel Edison, but I think they are discontinued, like they are not available anymore. And about the Arduino it's like on a different class. Arduino is a microcontroller, so have like low memory, low processing, but can like live more time on a battery operation. So they have like a different usage. So that's why you usually need like a single board computing that runs like an operational system, have more memory, and those kind of things like for a gateway use case. So they have like different use cases. Usually, for example, Arduino is more like end nodes, and Raspberry Pis are for gateways and local servers and those kind of things. Here.
Are you specifically tied to TensorFlow and Edge, or do you have enough of a pseudocode that I could put into another neural network chip?
Well, the models that I use, I think they are available on other libraries. Like you can use YOLO with PyTorch, and yeah, you can use the same architecture. Right now, the code is using TensorFlow, but you can use the same concepts, but with other libraries for sure. But right now, it's tied to TensorFlow. Sorry. Security between the edge device and that's a good question. Someone already made that question for me. Yeah, there's no security at all between the edge, the camera, and the Raspberry Pi right now. So someone enters the network, will be able to see all the cameras. Yeah, that's something that needs to improve at this project because yeah. Like to retrain the model and. Oh, gotcha. Well, right now I'm just discarding the images, but I can use like a QE in between to process those images, and like even if the process is slow, I can still like have a process that is just for capturing images and another process that is for image classification. This way, this process can keep running and getting images and putting on that QE, and the other process that is classifying images can run separately. Even if it's low, I'm not going to lose those images. But I didn't done that in this case. I'm just like getting images, classifying, and then go all over again. So yeah, I can potentially lose some images if there's too many images, or I don't know, if like I have 10 cameras and they will take like 10 seconds to process all the frames from all the cameras, I can lose some images in the way. But yeah, I can improve the architecture to not lose some images. Not PubSub, because PubSub needs to run in the cloud, but there are some projects like RabbitMQ you can run locally, and SQ. There are some good libraries for queues that you can run on a Raspberry Pi. RabbitMQ is a really good one. NSQ is probably lighter. And I think, oh, I have 1 minute. So maybe one last question. Someone else?
Considered using Home Assistant at all to manage your ESP?
I will tell you a secret. I use Home Assistant a lot in my house. And I love Home Assistant, yeah. But yeah, I can use like, get those labels and feed that to Home Assistant and generate some home automation rules. So yeah, I can definitely do that. And I think that's it. Well, I will be around the event, so anyone wants to reach me out, just. Thank you all for coming.